We're going to consider now a clarification on the mathematical aspects of these relations between orthonormality and completeness. We discussed it before for the case of a set of eigenfunctions of the energy operator, how they were orthonormal if we chose to make them orthonormal, and how that led to one equation, and then the statement that they were complete, in fact, led to another equation. And the two equations were very similar, and the wave functions that you were using had like two labels, a discrete label for the wave function sub n and a continuous label for the position. And in these two equations, orthonormality and completeness, there were sums that were very analogous and dual to each other in some sense. So I want to clarify this by redoing this in the context of something you know. Just orthonormality and completeness on a vector space, a real vector space, three-dimensional vector space, our familiar three space. So in this context, the mathematics will be a little simpler, and you will be able to appreciate why these two conditions are closely related. So I will talk about orthonormality and completeness. Very good. So we'll be speaking about a three-dimensional vector space. And in this three-dimensional vector space that we'll call R3, there will be three vectors. So there will be a vector v1, v2, and v3. The subscript indicating which vector it is. And moreover, given that there are vectors, I will put an arrow to be completely clear that these are vectors. The first vector, the second vector, and the third vector. So these vectors are going to be three nice vectors in this vector space, and each one has components. So I will write the components. So each v, so let's say m can run from 1 to 3, has three components, and they will be denoted as follows. We'll put Vm vector, we'll write it as Vm k ek, and this is sum over k. So what do you have there? You have the sum for every m, for 1, 2, or 3, the sum over k of, that also will run from 1 to 3, because they have three components. The first component times the first unit vector, the second times the second unit vector, the third component times the third unit vector. So these are our vectors. And now suppose somebody tells you, these vectors are orthonormal. So what does that mean? Well, it means that each one has unit length, and the dot product of them is 0 if you take two different ones, orthonormal. That's the condition that Vm dotted with Vn is equal to delta Mn. The Kronecker delta that is 0 unless m is equal to n. So this is a nice equation. Now we can write it more explicitly using the indices, because in fact, if you have these vectors here, the dot product is done by adding the products of the corresponding components. So this equation really is the sum over k of Vm k Vn k being equal to delta Mn. So that's the equation written explicitly. Now I want to write this equation in a way that is understood as a matrix equation. And the reason is that, as I mentioned before, there's two kinds of labels on this object V, the label K and the label M. And they run each over 3 values, so that is natural. There's 3 times 3, 9 values for this object. So we'll try to think of this as a matrix. So I will write these things as a matrix. So let me define the matrix V hat, and the hat tells you that I'm talking about a matrix. And it has components K, M, so I'll put them like this. The Km component of the matrix V hat will be, in fact, the kth component of the mth vector. So this is going to be my matrix. So you have a row index that is the component of the matrix. You have a column index that is the vector. So as a matrix, this is the row index and the column index. Focus on the column index. This would be V1, V2, and V3. The matrix, the column index, M, runs from 1, 2, and 3. So you can think of the matrix as putting the components in vertical fashion. The 3 numbers here, the 3 numbers here, and the 3 numbers here for the third vector. At any rate, this is what we will mean by this matrix. And now let's see what this equation becomes. So this equation over here is the sum over K of V hat Km times V hat Kn. I just rewrote these two things in terms of the matrix. This is equal to delta Mn. But now look at this thing. This is almost matrix multiplication. In a matrix multiplication, the second index of the first factor should be coupled together with the first index of the second one. So K is being summed, but here is in the first position rather than in the second. So I will write this as, using the transpose symbol, as sum over K V hat transpose sub mk V hat Kn. That's the left-hand side. And now you see that this is nothing else that the Mn component of the product of these two matrices. So this is equal to the V hat transpose times V hat Mn being equal to delta Mn. That's a nice equation. But in fact, it's even simpler. You can say that this just shows that V hat transpose times V hat is equal to the identity matrix. This is to say, actually, that the transpose matrix V hat is the inverse of V. A matrix whose transpose is its inverse is called an orthogonal matrix. That's not too relevant now, but it's a nice name, and you can recognize this kind of equation. So what it turned out was that the condition that the vectors be orthonormal allows you to think of the collection of vectors forming a matrix that happens to be an orthogonal matrix. So this is the first condition, orthonormality. We've translated it into a matrix equation. The thing that we want to do now is do something similar with completeness. So what is completeness? Well, the statement of completeness for our vectors is the statement that any vector, any arbitrary vector, can be represented as a sum of numbers times this particular vectors, that these vectors form a complete basis. So any vector, consider a vector A that in general has components AK, EK. This is a normal vector, just an arbitrary vector, and it has your Cartesian components EK like this. The statement of completeness is that there exist coefficients alpha, say m, such that this vector can be written as a superposition of the basis vectors we're working with. So the basis, the set of vectors that we introduced above, v1, v2, and v3, is complete if any vector can be written as a sum of this with some particular coefficients. So that's a statement that is complete. And as before, our goal is to turn it into a mathematical condition on the vectors. And this is done just like what we did for the case of the energy eigenstates. We have to sort of go a little bit in circles. We have to calculate the alpha m's and plug them back and see what we get. So that takes a little bit of effort, but let's do it. So the first thing that you observe is that you need to calculate the alpha n's, and that's easily done using the orthonormality that we had above. So what we do is multiply, say, Vn, the vector Vn, dotted with A, and we do it on the right-hand side as well. When we go to the right-hand side, we have the dot product of Vn with Vm, which is a Kronecker delta, and therefore the right-hand side just becomes alpha n. So that determines alpha n. You've calculated alpha n. The next step is to substitute the value of alpha n in here and manipulate this equation until we get a condition. So let's do that. So what is A? Now, from the equation here, we'll just write this. This is sum over m. The alpha m is equal to Vm dot A. And then we have Vm vector. And now we must start expanding this. So let's take the dot product and let's write these things in terms of the components that they have. So what is this? We'll have a sum over m, and we'll have more sums over here as well. I'll put sums over p and k. The sum over p for this dot product. What is this dot product? Is Vmp times Ap, the Cartesian components of each one. And we'll have the index k for this thing. So for this vector, it would be Vm k ek. Okay, so we've spread everything out, and now we have to collect it in a convenient way. The thing that we want to keep together is this thing. and begin to notice that while in orthonormality we had these two labels being different and summed over components, we're now summing over the different vectors. So this is something we want to keep in plain sight. So let's write these sums by pulling the m out. So we'll write the sum over p, or k, the sum over p, and then the sum over m of v m p v m k. Then we have AP, and then finally we have EK. All right, lots of indices, but we hope we can keep the ideas clear. So this thing, look at this. The A vector is written in this way. Now it looks fairly complicated, but the A vector was supposed to be AK, EK. And here we have the EK. So somehow all this thing must be giving you AK. Because if all this thing is AK, that's what the vector is supposed to be. This should be AK. But if this is supposed to be AK, and we're summing over P, what would allow that to happen is if this sum over here is delta pk. So then when you sum over p, it would turn this into an AK. So what this equation requires, that is the statement of completeness, is that this sum somehow be equal to delta pk. So we'll write here, you need that this sum over m, v m p v m k be equal to delta pk. So we've turned the condition of completeness into a mathematical equation. This should be true. Now let's use the matrix notation we introduced before, in which we want to see what this is as a matrix. It's also interesting, of course, to compare at this stage what we were saying, the two cases we have in which for orthonormality you sum over k, which is the index for the components. For completeness you sum over m, which is the index for the various vectors. So what is this equation? This is the sum over m of v hat pm v hat km. So this is the left-hand side. We can do the same thing here, in which we can switch these two indices at the cost of putting a transpose. So it's the sum of v hat pm v hat transpose mk. And now this left-hand side is recognized as the product of v hat times v transpose. So we've obtained that v hat transpose sub pk is delta pk. Or in other words, that v hat transpose is equal to the identity. All right, so we actually are getting to the point that we wanted to make. the whole statement of completeness has been boiled down as a matrix equation into this equation, that v hat times v hat transpose is equal to 1. And now you realize that this is pretty much this same equation. Why? You probably have learned that for finite dimensional matrices, if you have an inverse, it's an inverse from the left and from the right, both at the same time. So here it says that the transpose matrix is the inverse of the original matrix V hat. Therefore, both from the left and from the right, it should give you 1. So you realize that in fact, the condition that you had an orthonormal set of vectors that was equal to the dimension of the space. You had 3 vectors for a 3-dimensional space. When you have that, you already have not only orthonormality, but completeness. This is something we will emphasize when we study more deeply linear algebra. And you will see that in finite dimensional spaces, if you have an orthonormal set of vectors that is equal to the dimensionality of the space, they happen to be a complete set of vectors. This is a lot more non-trivial in infinite dimensional spaces, and that was the case for the functions we were considering, where we did our whole analysis for the psi n of x's, and one label was n, one label was x. So x can run over continuous values, n runs over infinite values, so that's infinite dimensional spaces. So in that case, the matrix property that you have an inverse from the left or an inverse from the right, one doesn't necessarily follow from each other. And that's why for these interesting cases of infinite dimensional matrices that correspond to our infinite set of energy eigenstates over a continuous variable, these properties are things that you should check separately, and you should get an insight whether you have both completeness and orthonormality.